Hello everyone, my name is Fang. Today, I'm introducing our work UCBoost, a boosting approach to tame complexity and optimality for stochastic bandits. First, I will introduce some background and motivations. Then, I will introduce our axiom and results. Multi-armed bandits can be viewed as a repeated game between an agent and an environment. It lies in the area of reinforcement learning and online learning. In this work, we focus on stochastic bandits. Stochastic bandits is nothing but the following model. At each time t, the agent plays an action at from a set of k actions. Then the agent receives a reward yat, drawn from some unknown distribution. The performance of bandit action for time horizon t is measured by the regret, which is the expected loss of the total reward collected by your axiom and one oracle that knows the ground truth. It is well known that the regret lower bound is in the order of log of t, and there are several popular axioms such as upper confidence bounds, Thompson sampling, and epsilon grading. However, the existing axioms has a complexity versus optimality dilemma in the real-world applications. In some real-time applications or large-scale applications, the computational complexity really matters. The existing axioms either are optimal but involve heavy computation, or simple but are far away from being optimal. A natural question is, can we design an axiom that can trade off complexity and optimality? Our results in this work provide a positive answer for this open question. Our UCBoost axioms can ensemble a set of weak but simple UCB axioms. We propose two solutions, one with finite set and one with infinite set, to offer trade-off between complexity and optimality with guarantees. As highlighted in the table and figure, the finite set version UCBoostD axiom can achieve regret bound of bounded gap to optimal lower bound with constant computational time. To be arbitrarily close to the optimal, our UCBoost epsilon axiom takes only log 1 over epsilon computational cost. To understand UCBoost axiom, we first introduce the generic UCB axiom. First, we define some distance function between expectations of two random variables over some bounded support theta. The distance function is non-negative, satisfies triangle inequality, and it is not necessary to be symmetric. A semi-distance function is said to be strong if it is zero if and only if the two arguments are equivalent. K of divergence is the well-known distance function, and we say a semi-distance function is KL dominated if it is upper bounded by the KL divergence. Now we are ready to introduce the generic UCB axiom. For each distance function d, the corresponding UCB axiom is the following. At each time t, play the arm with the highest UCB index, which is the largest expected q, such that the accumulated distance to the empirical mean is bounded by log of t. Note that n sub a of t is the number of playing arm A up to time t, and the bar of y sub a of t is the empirical mean of arm A up to time t. Theorem 1 provides a regret bound for the generic UCB axiom if the distance function d is both strong and KL dominated. The generic UCB axiom gives us some useful insights. The UCB kernel is the same distance function, and the complexity of UCB axiom depends on solving the problem P of D, which is maximizing the Q such that the distance between empirical mean P and Q is bounded by some exploration bolus delta. We can check that K of UCB is nothing but a distant function in K of divergence. It is computationally heavy because solving problem P needs iterative method. UCB1 uses the squared distance as kernel and it has closed-form solution. Actually, we can come up with some new semi-distant functions that are easy to solve. For example, Henninger distance and biquadratic distance. Theorem 1 provides regret bounds for these new simple UCB axioms. The lecture question is, can we ensemble these closed-form UCB axioms to a stronger one? To ensemble a set of UCB axioms, we first consider a set D of KL-dominated semi-distant functions. This set is said to be feasible if its envelope is a strong semi-distant function. A sufficient condition is that there exists one strong semi-distant function in D. It is easy to construct and verify a feasible set. Now we are ready to introduce our UCBoost axiom for a given set of distant functions. For each arm, UCBoost queries the UCB index for each distant function and takes the minimum one as UCBoost index. Then the axiom places the arm with the highest UCBoost index. Theorem 2 provides a regret guarantee for UCBoost D axiom if the set D is feasible. This result shows that UCBoost has the ability to boost a set of UCB axioms as its regret bound is better than any of them alone. Another insight is that if all distants in D have closed-form solutions, the complexity is constant. This allows us to control the computational complexity of UCBoost axiom. You may ask the question, why taking the minimum? Let's take a look at the philosophy of voting. Should we do majority vote? No. If the ordering is known, the best option is to follow the needle. So UCBoost takes the minimum, thus the tightest upper confidence bound. Consider this toy example with 3 simple UCB axioms and 3 arms. UCBoost takes the minimum UCB indices for each arm as UCBoost index and place the arm according to these UCBoost indices. The decision is different from majority vote. Let's take a larger geometric view of UCBoost. The kernel of UCBoost is the envelope of a set of distant functions. Taking the minimum is equivalent to solving the problem P with the envelope function. So the closer the envelope is to the KL divergence, the better regret we will get. Now we are ready to introduce a new semi-distant function that is very useful. It is a simple lower bound of KL divergence by dropping one positive term. However, it has a closed-form solution of problem P, and it is tied to KL divergence when Q goes to 1, thus allowing a bounded gap to optimality. The following corollary shows that if we take these 3 distant functions, the regret bound is 1 over E close to the optimal. The computation takes constant time for each arm at each run. Inspired by the geometric view of UCBoost, we designed a sequence of semi-distant functions to approximate KL divergence. To be specific, for any epsilon, we define a sequence of geometrically separated points. For each point, we define a step function that jumps to its KL divergence at a point. For each input empirical mean P, we construct a dynamic feasible set D of P that contains the step functions with jump points within certain range. For this range, the step functions can approximate KL divergence with epsilon. For range close to 1, the lower bound function can provide a good approximation. So the regret of this UCBoost epsilon axiom can be guaranteed to be epsilon close to the optimal. By using a bisection search trick, the complexity is log 1 over epsilon. Then I will introduce the numerical result. We ran the experiments in three synthetic cases. Case 1 is the basic case with Bernoulli rewards. Case 2 is modeling the cases in online recommendations with small expectations. Then we test our axioms in beta distribution, which is another typical distribution with bounded support. Here are the average regret results in three cases. We can see in the first row, the three simple UCB axioms are far away from the performance of KL-UCB, and no one dominates the others in all cases. However, UCBoostD axiom can ensemble these three axioms to be a stronger one, which is the red line in the figures. Then in the second row, we can see that the UCBoost epsilon axiom pushed the performance more closer to KL-UCB with moderate epsilon. The computational cost shows that UCBoost epsilon can achieve the same regret with only 1% of the computational cost of KL-UCB. This means that UCBoost epsilon enables 100 times faster response time or 100 times capacity of arms. Here are the takeaway messages for this work. First, we studied generic UCB axiom and proposed some new UCB axioms. Then we propose UCBoost axiom to ensemble these axioms to treat complexity with optimality. We offer two recipes, UCBoostD with bounded gap and constant complexity, and UCBoost epsilon with epsilon gap and log 1 over epsilon complexity. And last, this is the boosting framework, so you can bring your own semi-distant functions to try. This is the end. Thank you very much. If you have any questions, please feel free to contact me.